Good morning, Year 11, and welcome to another science lesson. Today we're going to look at calculating electrical energy. We'll start off by doing the do now. If you haven't done it already, please pause the video, go back, complete it. Okay, so hopefully you had the following. Oops, try and turn that on. Hopefully you had the following, the equation to calculate efficiency using energy. So your efficiency is useful energy out over total energy in. Okay, so useful energy out over total energy in. If you're doing power, it's your useful power out, very similar, divided by total power in. The efficiency of a light bulb that transfers 30 watts of electrical energy into 15 watts of light energy, we'll do 15 over 30, that's going to give us 0.5. 0.5. The efficiency of a spring that releases 20 joules of energy after storing 80. So your efficiency is 20 joules divided by 80 joules, which is 0.25. Please note there are no units and we haven't multiplied this by 100, so it's not a percentage. What is the efficiency of a ball that bounces up to a height of 5 meters when dropped from 20? Well, we could work out the potential energy of each one, but we can see that this is 4 times smaller than this, so it's got to be 0.25. It only gets to a quarter of the distance. Okay, so back to today's lesson. We're looking at the power and the energy transferred by electrical appliances. So we're kind of going off the spec a little bit here. We're jumping ahead maybe 2 or 3 lessons, but I want to do this so it can show us how to do some quite interesting efficiency calculations later on. So there's 2 situations you might have. So you might be asked to work out the power given this equation here. So power equals potential difference times current. So let's try and put this into a triangle so we can remember that. So P on the top, we'll put V over here, and we'll put I there. It's worth remembering that power has to be in watts, I for current has to be in amps, and V for potential difference has to be in volts. And we can, if you're given 2 bits of information, you'll have to work out the missing one like we've seen before. So we have a coffee machine that has a potential difference of 230 volts across it, and it draws a current of 8 amps. What power does it transfer? So P equals I times V, or V times I. That's 8 times by 230. Let's see if I can find the calculator. I'll use my phone. So 8 times 230 gives me 1,840. The unit is watts. You may need to convert from watts into kilowatts. So there is 1,000 watts inside a kilowatt. So if you're going from watts to kilowatts, you need to divide by 1,000. If you're going from kilowatts to watts, you multiply by 1,000. So if we wanted to rewrite this in kilowatts, I'd have to divide 1,840 by 1,000, and that would give me 1.84 kW, kilowatts. Notice it's a lowercase k, it has to be a lowercase k. Over to the other side of the direct instruction here, we've got an electrical motor. So an electrical motor is a device that converts electrical energy into kinetic energy. So if we put VIT in there, we're going to be able to get, we'll work out how much energy we're supplying to it. Not all the energy that we supply to it electrically is going to be transferred into kinetic though. We need to use this equation here. Energy equals potential difference times current times time. Pop that into our equation. So energy is going to be in joules. Time must be in seconds. So this is where they might try and catch us out by giving it to us in minutes or hours. This has got to be amps, and this has got to be volts. So let's see what they've given us here. So we have 6 volts, 0.5 amps on all that. They're causing problems for us already. We need to convert from minutes to seconds. I'm just going to multiply that by 60. So 1 minute is just 60 seconds. I'll rewrite the equation. V by T. V was 6 volts. Current was 0.5 amps, and that was 60 seconds. 6 times 0.5 times 60 is, I believe, 180 joules. So 180 joules of electrical work is being done by this motor. It's not necessarily being converted into kinetic energy or anything else, but we'll look at that a little bit later. Okay, we'll go through one more example. So this is a similar sort of idea, but it's slightly more tricky. We have a coffee machine, so this is La Pavoni Europica, a really good coffee machine, and the output is 2.53 kilowatts, and they're trying to catch us out already. If we flick back to the DI, we know that if we're going from kilowatts to watts, we're multiplying by 1,000. So I'm going to multiply that by 1,000 straight away, and that's going to give us 2,530 watts. Be very careful, they'll always try and catch you out like that. We have a mains potential difference, and it's asking us to work out the current. So we started off with this equation, P equals V times I, or I times V. We also had the triangle that looks like this if we needed it. We're working out current. So this is what's missing, this is what we're working out. We'll cover that up. We'll be left with P divided by V. So I equals P divided by V. The power, we're not going to write 2.53, we're going to write 2,530. We're going to divide that by 230. Back to the phone. 2530 over 230 equals 11. And it's current, so it has the unit amps, so 11 amps. And you can kind of use a bit of common sense here when you get your answer. So if you're working out the current for a normal appliance, it's going to be somewhere between 3 and 15 amps. Anything lower, it's not going to be a mains appliance. If it's anything bigger, then it's not going to be true either. So if it's something that you plug into a socket in your house, your current is going to be from about 3 to 15 amps. That lies in that range, so yeah, we're happy with that, 11 amps. Here we have a lamp. It's 24 volt power supply, 1.5 amps, calculate the power of the amp, so power of the lamp, sorry. Very, very straightforward using the equation straight away. This one, it's a little bit more complicated. We have a solar cell with a power of 2.4 watts. We know what its efficiency is, we need to calculate the useful power output. So this is very similar to what we did yesterday. This time you need to use information from the graph to work out the power. So remember, power is energy divided by time from our previous lessons. If you work out the gradient of this graph, it's going to give you the power. And finally, you need to use the graph below to calculate the power developed when the potential difference is 0.4 volts. So you will need to read off the current value for the potential difference of 0.4 volts and go up, go across, and then you're going to use the power equation from earlier. Last one, this equation is going to be power equals energy divided by time. We're trying to work out energy stored, so you're going to need to rearrange it to give energy equals power times time. But be wary, 25 minutes needs to be converted into seconds. Okay, thank you very much, Year 11. I'll see you tomorrow.